How does molecular substructure annotation help prioritize and interpret metabolomic data? How do communities shape both individual careers and the direction of the field? And what is the place of open science and interoperable tools in the future of metabolomics? These are just a few of the questions we address in this episode of The Metabolomist with my guest, Justin van der Hooft. Welcome to Season 5 of the Metabolomist podcast, where we dive into the communities that are transformed by metabolomics. I am your host, Alice Limonciel, and this year I will engage with scientists who not only use metabolomics, but who leverage it for the greater good. People who know that metabolomics is a tool that holds the promise of transforming our society, but who also understand that to deliver on that promise, metabolomics needs to be part of something greater. Projects, networks, infrastructures, they all form around a common goal and make use of the best tools at their disposal. So this year in the podcast, I talk to passionate people who build communities through any strategy, from grassroots movements to decades of networking. Join me to discover the creations of these community builders and how metabolomics is helping them advance their mission. It is my great pleasure to welcome Justin van der Hooft. I probably pronounced this wrong.
Well, you did a good job, Alice. Justin van der Hooft.
So I'm really happy that you're my guest today because it's really years in the making that we managed to have you on the podcast. We've known each other for a few years and we've met each other at different conferences and meetings. And I really love the work that you do using computational methods to really make the most of the measures that are made with the different instruments that people use for metabolomics. And so every year I like to have someone who talks a bit more about the computational aspects so we understand where the field is going, but also we can learn, especially from your work and also how you've been growing your team in the last years.
Sure. So, well, first of all, thanks for having me on your now very famous Metabolomics podcast. So it's also first for me to do a podcast. So in that sense, I also look forward to this interview. So, well, I started my metabolomics career, one could say, during my PhD here in Wageningen, where I now also work. And in particular because of a manuscript of the thesis that was reviewed by somebody in the metabolomics field. And I got a lot of feedback on how I could improve especially reporting of my results. And that really led me into the metabolomics field. And then I joined the metabolomics conference in Edmonton in Canada in 2009. And that is where I met quite a few people that I still now meet nowadays when I go to the metabolomics meeting. And so it is very nice because it kind of gives you an idea of a whole research family rather than, of course, they are colleagues as well. And some have become almost like friends. But the sense of this family is there as well because every 4 or 5 years a new generation starts and also grows into the scientific majority, just like myself. And then after my PhD, I left for Glasgow in Scotland, where I did my postdoctoral time, or most of it anyway. So there I kind of grew slowly more towards the computational side by doing more and more analysis and also collaborating with computing sciences, so Simon Rogers and Joe Wandy. And we will get to talk about that in a bit more detail later. And then after that, I returned to Wageningen, first on a shared contract with Peter Dorstein in San Diego, the US, and Manis Medema here in Wageningen. And then soon thereafter, I got my first, let's say, own grant, or that I actually wrote for the majority myself. And that was with the Netherlands eScience Center. And there you can already hear that it's more and more drifting towards the more computational side. And then in January 2020, I was able to start my own team here in Wageningen as an assistant professor. So that is now 6 years ago. It was a bit of a challenging time, as I think many of you will remember that soon after the January 2020, the virus also came to Europe, and all the education had to be online, and like we do as well now, by the way.
Yeah. Mm-hmm.
And that gave its own kind of challenges and struggles. So I'm really happy that nowadays we can do the teaching again in the classroom and have more personal contact with the students. And the same is true for the supervision of PhD students, postdocs, and the master thesis students.
Mm-hmm.
So by now, my team is consists of more than 10 different people that I supervise and co-supervise, PhD students, postdocs, working in different aspects of metabolomics and computational metabolomics.
Yeah, it must have been a really interesting time to start your group at a time when people basically can't meet each other. Must have been really difficult.
It was challenging. At the same time, the luck that I had or have is that in many aspects, computational work can be done behind a laptop. But having said that, I think we underestimate the importance of personal contact, right? And I think it's really important to not only talk to each other through screens, but also be in physically, like in the same room or at least close to each other, because you will hardly ever have a chance encounter like this, right? You always have to agree to meet, and these chance encounters, they often bring quite unexpected developments, new ideas.
Yeah, and I think especially when you build a new community. So community is the topic of this year for the podcast. But even at that scale of maybe 4 or 5 people, to build community, you really need to have these unprompted connections or interactions. Yes.
And here in Wageningen now, the difference is between now and back then is now I also see computational methodology related things on whiteboards where people have been kind of brainstorming about new approaches or projects. And that's very nice to see for me, because when I started here as a postdoc in 2017, September, the topic was there, but not so big, right? I mean, hardly anybody directly worked on development of tools. It was mostly left at kind of application or sometimes as a side project of a larger project. And now it is one of the main kind of directions that we do here at the bioinformatics group.
And maybe as a side note, just from my own career, so at the time when you were starting with metabolomics, I was as well. So 2009, 2010, we had our first metabolomics. We were working in a large consortium, and then we got our first metabolomic data set. We were really excited, but there were absolutely no annotations of the metabolome. So it was a lot of features, and we could see just mathematically that the changes in those features, we had a kinetic experiment, so we could see like the profile was changing over time. It was matching really well what we were looking at in the experiment, but we didn't know what any of those metabolites were. And at the time, our collaborators were like, look, we would love to do this, but it would take a whole PhD to annotate that data set, and we can't make that investment right now. And I think thanks to you and other scientists, there are now tools that make it much easier for scientists to annotate metabolomic data sets. So it's just to give an idea of like how far we've come in the last 15-20 years, that we went from we need to think of getting a whole PhD student to do that work to annotate a data set to now you can do it with a few pieces of software. And I think you will tell us about it, but you do have to be diligent about the assumptions you make, about the parameters you choose, so that you can guarantee the quality of the work you're doing. But still, now you can annotate hundreds, potentially thousands of features in one data set, right? So I think there's really been a lot of progress.
Yes, I think one of the driving factors for myself was that during my own PhD, it took me also a lot of time to kind of dig into one file, one profile, one hyphenated LC, liquid chromatography, mass spectrometry, and then tandem mass spectrometry, so LC, MS profile. I mean, I think I've spent like 2 months to kind of really almost spectrum by spectrum deciphering like what is in this tomato extract. And I mean, nowadays you wouldn't imagine that anymore, because you run the available tools and you get an overview, and then you start to kind of prioritize and dig in. But back then, I mean, what it did learn me is a lot about spectral quality, about what are real fragments, how do they
Yes.
look like. So it really allowed me to interact very closely with the data, and I still benefit from that nowadays in my supervision as well. So I mean,
I'm wondering,
yeah.
as you say this, I'm wondering, and I'm going to sound like a very grumpy old lady, but like, do you get the feeling that that's painful work, like really like being so close to the data, you just said like was something really beneficial for you? Do you feel like the next generations are less and less close to the data and maybe they don't have this kind of quality connection to the data that you had at the time because you didn't have the tools to do it any other way?
Well, yes and no. I mean, there are directions that are kind of shielding
Mm-hmm.
some tool. I mean, if you use tools that really take away a lot of this pain, I mean, on the one hand, it's
Yeah.
nice because you can more quickly gain insight in the trends and patterns in the data, in whether the
Mm-hmm.
data is going to lead you to somewhere interesting or not. But there's also tools that allow you to inspect different aspects of the process more in more detail. So the
Mm-hmm.
visualization. I mean, we with our team we had last year a review on metabolomics and visualization, and there we also highlight how different tools allow you to visualize different aspects of the metabolomics workflow. And what I think, what I took away from that is that, yes, at some point, if there's really important molecules in your data that you see annotations for, then you need to be able to trace back the original spectra, the original data that led to those annotations to make
Mm-hmm.
sure that you are on the right track.
And is
And
that, as you say this, I'm thinking perhaps it is the developers of the tools that we use then that kind of take this responsibility for us, that you decide where the cutoffs are made or where like which parameters can be decided by the user and make it possible or sometimes not possible. I'm sure you choose sometimes to make it not possible for people to do something because you want to prevent mistakes that maybe someone who's less of an expert could make. So I assume there must be a kind of responsibility when you develop those tools. Is it the case?
well, yes, of course, but it's a shared responsibility. As with anything, you can use tools for the better or the worse, right? So yes, there is a responsibility for developers like my team
Mm-hmm.
to ensure that there's full transparency on what different parameters mean and how they affect the end result. But there's also responsibility for the user to spend some time in trying to understand what these different parameters do and go
Mm-hmm.
beyond the defaults, especially also finding out what the defaults are meant for or intended for, because we have so many different metabolomics settings and disciplines and directions that it would be very coincidental if those defaults are
Mm-hmm.
indeed ideally for your case. Yeah.
Mm-hmm.
So
That would
yeah,
make you
shared
think like
responsibility.
Absolutely. And you could even think like for the users of a sticker like we have for alcohol, like drink sensibly, you could have something like analyze sensibly. That's like you don't just
Maybe.
put
Yeah.
all the responsibility on the developers that now you have a tool in your hands. You need to understand it and
Yeah.
understand limitations as well.
Exactly. I think that's a very, very good message. But as I said, I mean, there's also for the developers a responsibility to not pretend that it's not important to investigate some time in understanding what the
Hmm.
parameters are doing and also
Hmm.
encourage the users to do that. But do you think the future generations are, how will that go?
Hmm.
Well, I think on the one hand, I see also good developments because quality assessment becomes easier with some tools because the visualizations become more easy and the experimental designs that people are choosing are becoming more and more robust. There's also more literature on that. There's more teaching on that now. There's
Hmm.
workshops. There's a lot of resources that can help you to set up the right experimental design with the proper controls, both for, let's say, comparative metabolomics, but also for, yeah, more MS based, tandem MS based strategies.
Hmm.
So that is good. But what we should be wary about is that representation of all the results in a small table with some numbers. It's great. It's a great summary, right? And it may look fantastic, but those numbers come from somewhere, right? So there's a whole trace back of decisions, parameters, settings that led to this small table of numbers. And
Absolutely.
somehow we need to make sure that that we shouldn't focus too much on just single numbers in a table, especially when we also consider all the developments with AI, which I think we should mention in this podcast as well. And we see a lot of different uses in metabolomics of AI, and our team, we're mostly, I would say, working with machine learning, and we will come to talk about that, I think, in shortly. But also, of course, we keep an eye out on developments in AI, a bit similar to what happened in protein structure prediction, where AlphaFold really made a big impact. And I think at some point in the future, something similar is likely to happen in metabolomics, where the data will become so rich and well annotated and curated and harmonizable that we are able to learn and transfer information across data sets more easily. But until then, I think it's the hard work of everybody that is listening to this podcast and beyond to report their data in such a way that it will make it possible to compare results, to compare annotations, and to really transfer knowledge and information from one experiment to the other one.
Before we go and dive deeper into those methods that you've developed, we wanted also to take a moment to talk about any lessons that you learned from working with genomics and metabolomics. I know you wrote a paper about this a few years ago. There are lots of people, let's say, there are lots more people who are familiar with genomics than with metabolomics. So maybe we can learn from that, and also that can help the community to communicate better with that genomics community.
Yeah, so the paper you refer to is on the paired omics data platform. It is a really, it is a use case where the idea is that by registering and recording sequence genomes of bacteria, fungi, and plants to publicly available metabolomics data, that can help us to also develop the methods that kind of exploit this paired data set. So with a paired data set here, we mean in the paper that the data for let's say the bacteria is the sequence genome is of the same bacteria as the metabolomics data has been acquired from the extract of that bacteria. Sorry, I should specify that more clearly. And the whole kind of incentive was that we noticed how that information was scattered, not always easily retrievable from publications, or simply not there. And the thing is about developing methods that use this different heterogeneous data types and sources is that it takes a lot of time for people not involved in the experiments to make sure that these connections are correct. So if we can kind of help each other and make sure that the connections that are there are verified by the people that actually were involved in either the sequencing of the genomes or the measuring of the metabolomics data, then that can help us to make sure that all the public data that there is, that the connections that are there, that they are, that it can easily be retrieved. And that's where this platform is. That's one way of doing that, right?
Yeah, no, that's a great way to enable also the use of multiple omics together rather than just looking at your little corner.
And I think if you ask me, metabolomics and genomics, I mean, genomics, of course, started earlier, but you see that metabolomics underwent similar kind of process of the file formats. So there's still different file formats also in genomics, also in metabolomics. But you see that they get more and more a little bit interchangeable. You also see that making the data available in the beginning, there was not a thing in metabolomics, and now you see that there are different resources, repositories available, like GMPS Massive, like metabolomics workbench, like metabolites, that each have their own kind of pros and cons, but they all have a shared common goal, and let's say make the data available for reuse, for verification, validation of findings.
I think this harmonization is really a way forward, and it must be difficult when you work on developing methods to decide at what stage you want to have that more harmonized, or if you have to commit to a certain format and then you have to leave the rest alone, because I assume you want your tools to be usable by the whole community. So that probably complicates the work for you.
Well, I mean, there are different communities, right? So, and this paired omics platform is really targeting, let's say, the network product community where people are working with either genomics or metabolomics or both, because many also work with both, and they are interested in network product discovery. And there is a community interesting in this. We had a conference in Leuven not long ago in February from the EU consortium, Doctor Training Network, Magic Morphin, and there were like 120 people that also came together to discuss genomics, metabolomics, and also the computational tools to analyze this omics data. And we also spent some time, and there were some talks on integration between this genomics and metabolomics. So there is certainly a community that is interested in further developing these tools and also using them. And there's also, by the way, interest from companies, startup companies that also use now part of this toolkit to also mine omics data for network product discovery, for drugs, antibiotics, medicinal molecules.
Thank you. So I think we're ready to shift to our paper discussion. So we wanted to discuss two papers today. One is one of your earlier papers, and another one is a preprint that came out last year. So the first one is entitled Topic Modeling for Untargeted Substructure Exploration in Metabolomics. And I'm going to let you explain what that is, because already from the title, I have questions.
Yeah, so this is something that was started in Glasgow, where, as I told you already, from my PhD and also the early postdoc work, I realized it's a lot of work to annotate, elucidate all the structures in the data, especially if you look at plant and microbial data. I mean, even more so than in human data. There's so much different structures, and it is very hard to really characterize them all, the complete structures of all of them. But then I also realized, but what I'm doing all the time is also analyzing substructures or partial structures. So, for example, if you consider flavonoid glycosides, we have a flavonoid aglycon, let's say quercetin or camphorol. Those are recognizable scaffolds or backbones structures, and then they are decorated with sugar moieties, right? So what I basically did in my head was, okay, I see this peak, so that must be quercetin, or this I see this peak 285, that must be camphorol or an isomer. And I see this losses or this peaks, and that must be an hexose or deoxyhexose, etc. So in my head, I was kind of using the mass spec information to annotate the molecules at the substructural level. And then, of course, you can make new decisions. Are you interested in this particular group of flavonoids or not, right? Before you move on to full structure elucidation. Because to do that for all the molecules, it's just too much work. So you also see that in my current work, we say that we develop the methods to organize, prioritize, and annotate spectra in metabolomics data to get to the final insights. And so the substructure annotation is part both of organization, but also of annotation and prioritization, because if we can more quickly kind of annotate substructures, we can also make more quickly decisions on whether or not we're interested in this particular metabolite feature. So, and then I had a nice discussion and brainstorm with Simon Rogers and Joe Wonley from Computing Sciences in Glasgow. And there we realized that not long before we had this discussion, this topic modeling was introduced for texts. And basically it uses text documents, and it looks for often co-occurring words, more often than, let's say, than on average. And it assumes that if these words are more often co-occurring in documents, that they belong together as a topic. Let's say related to European politics, related to economy, related to sustainable energy. And we also realized that one document can contain multiple topics, and the same topic can occur in multiple documents. And that's a very nice analogy to substructures in molecules, because one molecule can contain one or more substructures, and also the substructures can occur in multiple molecules, because nature, I think, is quite efficient. If something works, it will be reused and it will be reinvented and built upon, right? So with that information, we decided, let's give it a try. Let's apply this topic modeling on the MSMS or the tandem mass spectra, and let's see what happens. And I still remember that at some point, not long into this trial phase, I opened the file and I could see the two peaks, that 119 and 136, that kind of belong to adenine, the base, right? The purine or pyridine. You can correct me.
I never remember. I always have to check it as well.
Yeah. So, but I still remember that I saw that combination and I realized, okay, this could really work, right? And of course, now, 10 years later, quite some groups around the globe have been using it, and it's still used in discovery of groups of fragments, losses, or a combination thereof that belong to a specific substructure or scaffold, to help us to more quickly annotate, prioritize the data in metabolomics profiles.
That's a really great method. And I love this about computer science, because you often see these methods just shifting from one field to a completely different field, as you explained now with the document reading. And it makes sense, because we also, as humans, we project the structures and the patterns that we understand. We project on many different questions and things that we look at. So it makes sense that the same logic applies to different things, and also that the way that we build our text is somehow similar to the way that our biology is built. I love this kind of parallels. But when you come to the computational techniques, then you can really put it in action and see how much you can leverage from these parallels that you can build with the same logic. Thank you for explaining this, I have to say, by the way, in a way that I could understand. So thank you very much. And so I understand that really this method now, you still use it. It's still, is it the basis of what you still do, or is it just one of the ways that you do what you do?
I would say one of the ways, right? I mean, in our current work, we are also further building on the molecular networking principle that has been introduced by Peter Dorstein's lab in 2012 for the first time. And so we are also continue to work with that. We are also exploring mass spectral embeddings, right? So the more without this direct edges or connections between the features, we put all the features in a chemical space, and we try to model that space in such a way that the areas in that space, for example, are connected to chemical compound classes or to other chemical information, so that when we look at this chemical space, we get a sense of what our metabolomics profile may contain, right? So those are other directions, but for sure, because the substructure information also can help us to link from the metabolomics back to the genomics, right? That has been one key driver to also continue this work. And the other one, and there is a recent preprint on that as well, is to use it as the substructure patterns as spectral alerts for non-target screening. And I'm just back from a conference in Switzerland on non-target screening. And actually, if you think about that, we are looking for contaminant residues like drugs or pesticides in samples where they do not belong, right? Or where we don't want to see them actually. But also those molecules, they have often a scaffold, and of course there are transformation products because of the microbes in the environment or because of photochemical reactions. But then you also get a group of molecules that are connected through the common scaffold, or at least structural similarity. And so what we did is also to use the new version of MSTLDA to help us to create a curated set of 50 spectral alerts for pesticide screening. This is
Yeah,
very
that's
good.
great because as you were explaining this, I was also thinking for exposomics. I mean, we call it maybe more exposomics for human exposures, but I mean, it's the same idea to find pesticides, whether it's in plants or in animals or in humans. It's a really clever approach because a lot of those chemicals have very peculiar structures, sometimes things that you wouldn't even find in nature. So that must make them relatively easy to find. Some
Yes
of
and
them.
no, because
Yeah.
as long as we don't really fully understand how mass spectrometry works, in the sense that we can fully predict what
Yeah.
happens to structures inside the mass spec, and
Hmm.
also how much information we really can get out of this spectra, right? Then it may still be a challenge to recognize specific kind of molecules in a
Hmm.
very complex background matrix. Yeah.
Now, I
Yeah.
noticed that a lot of your work is focused so on agricultural topics, so plants, bacteria, fungus, and that's the field where you develop your tools. But I'm sure there are lots of people in human health, animal health that also use these tools. But I'm wondering, do you ever need to develop specific adaptation specific, are there specific requests to these mammalian models that you would have to add sometimes or that demand specific attention?
Well, I mean, I always say the mass spec doesn't really care what you inject into it. Well,
Hmm.
of course, if you start to clock it or whatever, then it will complain. But
Hmm.
so it's the context that matters, right? If you're
Hmm.
interested in mammalian metabolites, then use the spectral libraries that contain mostly
Mm.
mammalian reference data, and use the
Hmm.
structure databases that contain
Hmm.
the relevant molecules, metabolites, so that when you do your annotation pipeline,
Yeah.
they will show up.
Hmm.
And of course, if we get more and more reference data available, then you can also start to train models specifically
Hmm.
on the mammalian part of the metabolome, or on the
Hmm.
microbiome part of the metabolome, or on the plant part of the metabolome. That is possible. But I think
Hmm.
we can also start to create more curated motif sets that are dedicated to specific parts of the metabolome. We already started that. One of the follow-up papers of the first paper in 2016, which is, by the way,
Hmm.
10 years ago now, was also MotifDB, where we started to also share several sets of curated motifs. Back then,
Hmm.
mostly curated by myself, but we hope also that the new version that we introduced in the preprint last year will also yield renewed interest in jointly, as a scientific community, building up curated motif sets for other species, other
Hmm.
sample types, etc., etc. Yeah.
And maybe it's a good place to go to the other paper we wanted to discuss, which is much more recent from last year. I think to this day is still a preprint. So the title is Large-Scale Discovery and Annotation of Hidden Substructure Patterns in Mass Spectrometry Profiles. What do you discuss in this paper?
It's
Yes.
like a completely renewed version of the tool. One of the challenges of academic software development is that we normally don't have like a full-time software engineer working on projects
Hmm.
to make sure that the code remains active and stable. And also MSTLDA, the first version, is a typical prototypical example of a tool base or code base that grew organically, right? Very natural. So on the one hand, you could argue that it's very good because it leaves a lot of room for exploration, but at the same time, it becomes harder and harder to add new things because, when you add something here, something may break in a completely
Hmm.
different part of the, let's say,
Yeah.
code base or tree. And
Hmm.
that also means that it becomes harder and harder to kind of work with it. Luckily, I had two PhD students in my team, Rosina and Jonas, both working on different projects, but both very much interested and kind of driven to work with substructures, one for natural products discovery, one for the spectral alerts in non-target screening. So
Hmm.
they teamed up, but together with Joe Wandy, and he worked on a new version of the visualization app. We upgraded MSTLDA, but actually created a new tool from it. So the whole code base is now based on MetaMask, which is a Python package that handles mass spectrometry data with all well-tested functionality to read in the data to work with it. So instead of using our own custom functions, we rely on a software tool that is also maintained by the community and that also more people are using. So if things break, there's a more urgency to also repair it. Yeah. And also a different LDA algorithm has been implemented to make everything more scalable, because we realize that 10 years down the line, the data sets are growing. People no longer want to do it on a few hundred spectra, but often on 10,000 or even 100,000 spectra.
The demand has changed a lot, I guess.
Yes. But that also means that the number of motifs or master motifs you generate, the substructure patterns, it will also grow. And one thing I didn't really tell you yet about this topic modeling, that it sounds fantastic and it is very nice, but it doesn't give you an annotation itself, right? It gives you the groups of words in text, or in our world, the group of fragments or losses or a combination thereof that are often co-occurring. So it's still up to you as user then to annotate it, right? And of course, if you have a lot of domain expertise, then you can do it already from the top of your head, or you can look up in spectral libraries the peaks and kind of, start the process of
be critical of what you read and make decisions based on that. Yeah.
But what we also did is now implemented a master motive annotation guidance where you can get some help by leveraging the larger spectral libraries as part of this motive annotation process. And as a final thing I think is worth mentioning is, because now there is more and more data, we also made it compatible with this new mass spectrometry query language called MassQL. So if you have a pattern, it will be also much easier to then search a large amount of data with that pattern to see where else do you find this particular motive or pattern.
Yeah, that's a very useful thing, of course. Yeah. We're ready to move to our last big topic, because as I mentioned, this year we talk about community building. So you're really, as I researched a bit your past in preparation, I discovered things. I thought I knew a little bit about your career, but I missed a few things. Especially, you mentioned it at the beginning. You were part of some of the early networks in the Metabolomics Society, and I learned that you were part of the first team of the EMN. Can you tell us a bit about? Because of course the Metabolomics Society is a big community in the metabolomics world, but what made this EMN network come up, and what did you feel that it was needed in the bigger community, something for the early scientists, early stage scientists?
Yeah, so I think what people realized, the PIs in, let's say, 2009, 2010, and then 2012, 13, when it then started to come off. I forgot the exact year now that it all started, but I think it was 2013 or 14, right? Is that like myself, right? I mean, now I'm 5-6 years into this group leader position, and slowly you become more. There's more and more distance between you and the career stage that most of your team members are in, right? So and it's very natural, but it also means that the type of questions, the kind of you get more and more distance, and of course I will do my best to answer all the questions and share experiences. But let's face it, I mean, the world is changing, so people working now on the machines, they use different software again, different options, and it makes much more sense to discuss that and kind of find people that are in a similar career stage to discuss that and help each other. And I think this early career networks like the EMN, like we also started young NMC, Netherlands Metabolomics Center, which is now the young BMC, Benelux Metabolomics Center. So another example of a community in the metabolomics world that has been very active over the last years. So what I see is that if you start to give the early careers the trust and also empower them to organize things with and for themselves, you see a lot of nice initiatives and things growing, right? For example, back then, I think it was in 2015, I started together with fellow committee members from the EMN this webinar series. And it's very nice to see that it's still ongoing, right? After 10 years, there's still every so often a webinar with people from the field where people are listening to, it's recorded, so people can also go back and hear from experts around the globe on different aspects of metabolomics. So that certainly has inspired also other people.
And I think also for these people also it creates community for them. So it's also nice to see that you and a few friends, basically, because I think you become friends as you do this, started this movement, for example, with the webinars, and now it's in the hands of completely different people, but who also work together. I think it's a beautiful dynamic, and it's really important.
And across the globe as well, in the case of the early career members network of the Metabolomics Society, which I think is also nice to see that despite all the current turmoil, that people are still able to work together, even they come from different countries, different backgrounds, different expertise. So I hope we can continue to do that for a long time, but also more locally, right? Where in the Benelux, Netherlands, Belgium, Luxembourg, there are quite several groups that work on metabolomics. Some are bigger and but some people are working on their own as part of a larger team or group. And they are involved in metabolomics. And especially for them, having these local communities is also very important, I think, because you can connect with other students that have similar questions, similar situations, and also help each other.
Yeah, no, I think it's great. I know I benefited from a network like this because I was in European projects, and it's a similar vibe with people from different countries and different styles of leadership also in their own labs. So some people feel a bit less lucky than others sometimes, and they can also get some support from their peers. So I think it's everywhere where we find community is really something that is good for the soul, for the people involved, but also helps the field rise together and helps the field benefit from the having several brains and I would say also hearts getting together and building something together. There is one community you're a part of that I would call, I'm not sure if that's how you would call it, but the open science community. And I know it's very common for people in computer science to really push this aspect of open science. So for that community specifically, what is important there, and why is it such a fight that I see so many computer scientists putting forward?
Well, I mean, if we think about the importance of open science for especially computational groups, I think it's first and foremost that without any data, they cannot develop tools, right? So let's face it, right? So of course they will be advocating for open science because it means that they have access to data that they can develop and test and validate their own tools and models and resources on. So, but I think it's not only that. I think it's all open science also helps to people can reproduce or start to reproduce your results. They can take your data and ask different questions, right? And you see a lot of tools now that allow you to reuse data and ask different questions. Yeah. For example, there has been this discovery of new bile acids, right? Mammalian metabolites. Well, co-production of the microbiome and the mammals in this case.
Teamwork.
But anyway, I will leave it up to the audience to decide whether they're mammalian, microbial, or a co-production,
or both,
or everything. Yeah. But this discovery, right? I mean, it brings together a lot of developments, right? Not only, we realize that there are these new metabolites, right? So, and we realize the importance of the microbiome, but then using all this infrastructure and the tools that were developed and this MySQL language and everything else, the fact that this this GPS Massive and other resources came out. So now they could also come back and ask the question like, hey, but hang on, did we actually see this before? And then suddenly thousands of features
Mm-hmm.
kind of were annotated with, okay, another potential new bile acid. So all that data, and that wouldn't have been possible without kind of open science, because then that data was still somewhere in a drawer or deleted and not
Mm-hmm.
accessible. And now we can
Yeah.
actually start to really see the impact of this kind of new discoveries as well.
Mm-hmm. Thank you. Are there other forms of community that you're a part of that you want to discuss?
Yes, I think there's one community that I also like to mention, also because quite some work of my own work has also found inspiration from there. This is the Dagstoel community around computational metabolomics. So as of
Mm-hmm.
2017, I've been a regular visitor of this particular seminar series, and actually the last time and the one that is upcoming next week, I'm also co-organizing. And
Mm-hmm.
it is really an opportunity to meet with 40-ish people, both experienced but also new and upcoming talent in the field of computational metabolomics, both methods developers and also suppliers, users, and also often some people from industry that all together kind of brainstorm. And
Mm-hmm.
for example, the concept of mold enhancer, which is another tool that I'm proud of because it brings together a lot of the different tools, makes them available together in one network, and this whole concept is still used by the community quite heavily. And that idea and the concept and the paper, it all started in this German castle in
Mm-hmm.
Dagstoel, in this 2017 meeting where we sat down together with a beer and laptops, and we started to
Mm-hmm.
kind of discuss how can we make this whole scattered analysis, different tabs and browsers, more easy for people. And then we kind of came to this mold enhancer concept where the different annotation layers came together in one network.
Mm-hmm.
So library matches, master motive patterns, and everything.
I can also attest to that. The Dagstuhl meetings are really, I was there a couple of years ago, you invited me, and it's really a beautiful, it's like a retreat, and then people who all want to take that community somewhere just brainstorm and find ideas of how they can work together, how can they bring other people together. It's really a beautiful initiative. I'm really happy that you continue this.
Yeah, exactly. And I hope it will be continued also in the future.
Yeah. So a last question about the communities. So you're part of a lot of communities, and maybe I would ask you about the metabolomics community, but you can choose a different one. But where would you like to see your favorite community, let's say, in 5 or 10 years? Like where would you like this common movement to take us?
And maybe it's true for most larger communities. I hope we can find the right balance between exploring new things and continue to develop our own favorite pet tools, but also make sure that those tools and resources keep talking to each other, right? Much like humans in a community, right? Without connections, without their interactions, there is no community. And what you see happening is that we all have our favorite go-to tools and frameworks, and that's also true for my team and myself. But at the same time, I think it will be crucial for success if we keep communicating and make sure that the input and the output of these tools are somehow talking to each other and compatible, so that when a good new idea comes out, that you can also use it and reuse it as part of other pipelines. And I think the amount of work that goes into that now is maybe underestimated. For example, we were able to send Nick de Jonge. He recently graduated in my team, so as a PhD student. And we sent him to Prague to also there, together with the MZMine people, integrate MC Deep Score 2 into MZMine. So that is now kind of integrated, compatible. So people who use MZMine can also benefit from Amstel Deep score. But
That's great.
if you think about the amount of work and time that goes into that, then I think we can still try to improve and make things even more easy to integrate. Yeah.
Thank you. That's a beautiful goal, I think, a community of tools that can work with each other just like we work with each other. This takes us to the last question for this episode. What's your favorite metabolite and why? To be fair, I asked you that question in Valencia 4 years ago, and you had a few already. So has it changed?
Well, I thought about it, and I will give you a different favorite one because why not?
Sure.
Right?
That's allowed.
The one I will mention now is called geosmin, and I think most of you will have smelled it. So if you think yourself to like going outside during or just after a heavy rainpour, and you start to smell, and you have smelled this earthy kind of odor in the air, then that is geosmin, right? So produced by bacteria, in particular Streptomyces. They produce this when water is released or when they are close to water. And geosmin, it comes from geo, the earth, and the smell, right? So the smell of the earth. And I thought it is a very nice molecule to mention because it's rather simple, 12 carbons, 22 hydrogens, and 1 oxygen. But it has this very peculiar smell.
Yes.
Mammals are very sensitive to it. We don't know exactly why, but presumably because it may have led us to sources of water. And as we all know, clean, good water is a pivotal kind of condition for us to thrive and live. And I also felt that it's nice because, first of all, it's also volatile and it's not something that I typically work with every day. So it's kind of another perspective. And it's also a molecule that is kind of facilitating inter-kingdom communication. I mean, this bacteria, they emit something that then mammals, we can pick up and make decisions on. And maybe as a final note, I think it's also nice to stay connected to the earth and kind of make sure that we value all the life, including the bacteria that are in the soil, also during our work. So I felt that nicely came together in this small molecule called geosmin.
Thank you. Thank you very much for this choice. I had no idea that there was a molecule responsible for the smell of summer storms, which is it's really, really interesting. Very good.
It's one of the main constituents of. I mean, there's more, right? There's some oils.
I'm sure,
also.
of course. Yeah. But to know that there's one that has this specific relation to it, and I also love your take on it in terms of communication to other species. We get a lot with volatile compounds, so it's really, really interesting. Thank you very much.
Thank you so much for the opportunity, Alice.
Thank you for listening to this episode of The Metabolomist, where we explored one of the many communities that leverage metabolomics for the greater good. To make sure that you don't miss out on our next episode, you can follow the podcast on your podcast app or go to themetabolomist.com and register to our newsletter. Until then, I wish you to get to use metabolomics with the same passion and the same dedication as my guest today, and don't hesitate to reach out to me on LinkedIn at Alice Limonciel with your thoughts on today's episode.